Greetings, everybody. I want to make a video that goes a little bit beyond just calculating probabilities. We've already done many types of problems with drawing cards or rolling a die that involve calculating the probabilities of a certain outcome. Like we might say, I think this is one problem that we've looked at. Can you calculate the probability of rolling an even number on a die? Okay, so that involves just calculating the probability or the odds of that event happening. But what if we have a scenario like this where we have a game where depending on how the roll works out, we could win or lose. So not only is there a probability of rolling any given number, okay, but there's a win or a loss associated with the roll. So I have here both wins and losses and probability all happening in the same scenario. Okay. Now the way I'll show that to you is by getting you to imagine a dice game. Okay. So we pay $50 to roll a die. If we roll a 1, we win $250. So we pay 50, we roll it. If we win, 250 is handed right back to us. Okay. If you roll any other number, meaning 2 through 6, then you win nothing, meaning you lose the 50 that you paid to roll it. Okay. All right. So hopefully, that's simple enough. You can imagine that. You could even get a die and roll a few times and kind of see how that work out with your long-term wins and losses. So a little bit of a hint about what's to come, the expected value, this number that incorporates the probability of the different rolls with the wins and losses associated with those rolls. What that does is allow us to see what our long-term wins and losses are going to look like, most likely. Okay. All right. So now the way that this fits into our class, as far as the bigger picture goes, is with this thing called a random variable. Now, since I've already introduced the game to you, I'm going to say, well, here's what the random variable is going to be as I conceive of this problem. Okay, I want the random variable x to be the net amount won during one play of the game. Okay, so already you might see, okay, that represents like that we could lose 50 or we could win however much we win. So here's a little table that puts it all together in terms of the probabilities of the different rolls and the wins and losses associated with rolling those numbers. Okay, so x, being the net amount won during one play of the game, could be negative 50, meaning that if you pay $50 to roll the die and you roll a 2 through a 6, you just lose the 50. Okay, so that's why I put it as not just 50, but negative 50. So that's one value that the random variable can take. The other value is that it could be 200. Now the question says the net amount won during one play of the game. Okay, so I know that it says you win 250 if you roll a 1. Okay, so you roll this number right there, you get $250 handed back to you. But if that happens, you're only up 200. Okay, because you spent 50 and then somebody handed you 250 back. You're only 200 above where you were before the play. So that's what I mean by the net amount won during one play. Okay. All right, so that's the values that the random variable could take. If the random variable is the net amount that I win during one play, it could be negative 50, meaning I just lose, or it could be 200, meaning that I win. What are the probabilities associated with that? Because there's the wins and losses, that's what the random variable is tracking. What about the probabilities? Well, probability of losing is 5 out of 6, because there are 5 ways to lose out of 6 total possibilities. Okay? You roll a die, there's 6 things that can happen, and in this case, losing, there's 5 ways you could lose. That's why it's 5 out of 6. And winning, okay, that's 1 out of 6, because again, there are 6 things that can happen when you roll the die, and there's only one way to win, so 1 out of 6. All right, now my first question, can you calculate the expected value of this random variable? So our formula for that, for any problem that asks us for an expected value of any random variable, is the value of the variable times the probability of that value. This symbol means we're going to add up all of those. So I take the first value times the probability plus the second value times the probability. It's going to look like that. Okay. So see, maybe you can imagine, or maybe you write out what that is real quick. I'll write it out and I'll resume the video. Okay. So now I've got it written out like this. I need to calculate the value of the variable times the probability and add all those results together. So the first value is negative 50 times the probability of that happening, 5/6, plus, remember that symbol, the summation symbol means add results together, 200, the next value the random variable can take, times 1/6. Calculating that, I'll get 8.33 if I round to the nearest penny in this case, since our number is money. And it's negative in addition to that. So negative $8.33. Okay, so what does this number tell us? I said it's a way of incorporating the wins and losses with the probability of them occurring. What that tells us is it's a prediction of the long-term average win per play. Okay, so here's what I'm saying. You might sometimes lose 50 and you might sometimes win 200. And you can imagine, I roll the die and I roll it and I roll it and I win and lose sometimes, right? Depending on the roll. But in the long run, as I play more and more, if I average out my wins and losses, it's like I lose $8.33 per play. I know sometimes I might win way more than that, but because I win so much less frequently, most likely, than I lose, then it's going to be an average loss per play of $8.33. So that's what that number means. Now, you might not be like this, but I am like this. I'm kind of curious to test things. I want to see, is that really true? So I have to tell you, what I'd like to do is just roll this dice a bunch of times and kind of pretend I'm playing this game and see, like, well, is that really true? If I roll and I pretend I win or lose and I average out my grand total, then is it really going to be like losing $8.33 per play? I'm curious. Yeah, because I could do that. I could play this game and see how it works out over many plays, and I could see if this number seems to be true. So at least I'm curious to do that, and I think if I did that, like if I was learning this, I would probably understand it better. So, well, I think actually though, it would, this is a long prediction of what's going to happen in the long term. It's not a very good prediction of what will happen if I roll the die 4 or 5 times, or even 10 times, or maybe even 20 times, okay? It's for the long term. So I would have to roll the die and kind of pretend to play this game a bunch of times. So there's a way I can do this. In StatCrunch, if you go to Applets, and remember StatCrunch is included with my math lab, and then I go to simulation, it simulates dice rolling, okay? And then I could enter in the specifics of how I want it to work. So in this game, I'm saying, oh, I got a 6-sided die, and I'm just going to roll one of them. That's the way the game was. And I'll just do compute, and what it does is give me the option to roll it 1,000 times or 5 times or 1 time, and it will just give me the results. Okay, so I'm going to say like this. So this is a simulation of if I roll the die and each side is equally likely to come up, how many 1s, 2s, 3s, 4s, 5s, and 6s I'm going to get out of 1,000 rolls. So for example, what this is telling me is, just based on a simulation, as if I was really rolling this, I would get, one possibility is 153 rolls of 1, 167 rolls of 2, 165 rolls of 3, and so on. I'm curious then, can I show that this number has some validity to it? All right, can I pretend like, all right, I won $200 153 times because this is telling me that I would roll 153 ones, and then all the others are the losses. Okay, so let's try that out. I want to see like what the long-term average there for 1,000 rolls turns out to be, and let's see if it's a good prediction of that number. Okay, so I'll pause the video again and I'll show you my results and we'll see. Okay, All right, so here we are with the results of the simulation. Quick disclaimer, before I paused it, I was gonna do 1,000 total rolls. I decided to do 2,000 because, well, after all, the expected value is a prediction of the long-term average win per play. So how long is long term? Nobody knows until you start rolling the die, okay? So I did 2,000 rolls, and here are the results. I have 332 wins. I rolled 332 times out of 2,000. And then here are the numbers for rolling 2 through 6. For example, for 6, it says out of 2,000 rolls, I rolled a 6 313 times. Okay, now I want to take those numbers. So that, according to that simulation, that's 332 wins at $200 per win. Whoops. And that's a total win of 66,400. And then with the remaining rolls out of 2,000 being 2 through 6, that would be 1,668 losses at $50 each. So a total loss, if you multiply those together, of 83,400. Now, I said that the expected value is a prediction of our long-term average win per play. So to figure out what that number would be if I actually played this game 2,000 times, if you can imagine that, that would be this. Total loss is 83.4 and my total win is 66.4. To figure out my net win for all those plays, I have to say 66.4 minus 83.4. Okay, so that's a net loss. You see, I lost more than I won. In fact, it's a net loss or a net win of negative 17,000. Now, I said that, like, if we rolled the dice a bunch of times, then we should be able to, give some truth to this number, that this number is a prediction of what would happen in terms of our average win per play if we rolled the dice a bunch of times. Okay. And like here I'm getting negative $8.33, like it's prediction that I'm going to lose $8.33 per play on average. And then this is number 17,000. Well, to get the per play average, I have to say that, well, my total loss for all 2,000 plays was 17,000, and divide that by 2,000. If you do that, then we'll get negative $8.50 per play. That's my total loss over all the plays divided by how many plays there are. So on average, we lost $8.50 per play in this game. Now, on no one play did we lose $8.50. We either lost 50 or won 200. But if you average that out over all the plays, that's what it turned out to be. Now, do you see these numbers are close? The prediction was if you play for a long time, that this will be about what your average win per play is. And then here I simulated rolling the die 2,000 times, and on average we actually did lose $8.50. Those numbers aren't equal to each other, and they're not, they're close, but it's not like this number and that number are the same. How do I explain the discrepancy? Well, it's all for the long term, okay? Lots of things can happen when I roll this die. I could roll a 1 every single time. That's very unlikely. But what happens in probability is that the more times something happens, the more the probabilities work out to be what we conceive them to be. So like I'm saying, I'll roll a 1 out of 6 times. But like I said, I could roll this die and it's possible that I roll a 6 every single time. But if I keep rolling it, the probabilities will even out such that I roll a 1 about 1 time out of 6. So in our simulation, that's what it does if I keep going. If I keep rolling the die and keep rolling the die, I will see that these numbers, you tend in the long term, and nobody knows how many times you have to roll the die to actually see the long-term result. Here I did 2,000 times, but in the long run, we'll see 5 out of 6 odds for getting a 2 through a 6 and 1 out of 6 odds for 1 out of 6. Okay, that's called the law of large numbers. Okay, so there we have it. There's my expected value, which is very easy to calculate, and I really hope that me doing the simulation and vindicating that expected value with the actual plays helped you see what it's supposed to tell us. You might think it's ridiculous to roll a die 2,000 times, but when you hear that, a certain gambling game has an expected value, like, well, that's what they mean by it. If you play a bunch of times, your long-term average is going to tend to this number. You might not even have to play it 2,000 times. It might be much less than that. Okay, all depending on how close the loss and the win are together. Now, let's look at this. So we got a net loss on this game. Most likely as we play this game more and more times, we're going to approach losing about $8.33 per play. But could we turn the problem around like this? How much would you have to win to break even over the long term? Okay, what would that have to be? So in that case, I'm framing the question like this. How much would you have to win for rolling a 1 for the expected value in this game to be 0? So that would be long-term break even. All right. So I will throw that question out to you. Have you consider it? And I'll pause the video and write down how we would phrase that question in terms of an equation and then solve it. Okay, here's how we would phrase this question and set up an equation. So I already know that the loss is settled at -50, and I'm trying to figure out, well, how much would I have to win for the long-term expected value, or the expected value, to be break even? Okay, 0. If it was negative, it's a long-term loss. If it was positive, that'd be a long-term win. So I got -50 for the loss with 5 out of 6 probability. Plus, I'm going to say that we'll let y be, this number right here. This what was 200. If I only win on my table 200, then I'm going to have a long-term loss per play. So I'll let it now be y, and we'll solve for that number, times 1/6. So this is my win times 1/6. Okay. So if I do a little multiplying, I get 50 and 5, that's -250/6, and y times 1, that's y/6. Move the 250/6 to the other side, it now becomes positive 250/6. Multiply both sides by 6, I get y to be 250. Okay, so this number on my table would have to be 250, for a long-term break even to happen. All right. Now, but I'm going to give you my answer is I have to win 300 for rolling a 1. So the game would have to be presented to me like this, that in order to break even in the long term, I would have to, the game would be described as being handed $300 if I roll a 1. I still pay 50, but then I'm handed back 300, okay, if I roll a 1. Why is that? Well, because, for our random variable, if our random variable is the net amount 1 during one play, if I'm said that I'll win 300, then my random variable being the net is going to be 250. Okay. All right. So that number needs to be 250 to break even over the long term. And then it's described to me in the game that I would win 300 if I roll a 1. Okay. I'll leave you with one final thing. I did say it already, but the expected value is a prediction of the long-term average win per play. We could try that out and see how it works out. Casino games are sometimes described in terms of their expected value. It's, I haven't vetted these numbers, but they think they are realistic. Casino games have a negative expected value. The players are expected to lose in the long run, meaning if you might win sometime and lose sometime, but if you calculate your average win during a play, I put win in quotes because the long term is going to be negative. Then we see roulette has, negative 5.26%, average long-term loss. Okay. And notice it says long run, right? I did tell you that it was a long run prediction. It doesn't predict any single play or even lots of plays. It's long term. Okay. Blackjack, slot machines, and so on, they have this negative long-term expected value. Yes, the players are, over the long term, over the long run, going to lose. That's the way that it works out.